All right, Ashwin, you can start. And maybe everybody else can switch off their videos.
Okay. Am I audible and is the presentation visible?
Yes, you're audible and it is visible.
Okay, I'll start. So, good afternoon, everyone. I will be presenting on the topic of system identification of a MMG ship maneuvering model using support vector regression. So, the contents for today, I will briefly introduce what is involved by using system identification using support vector regression. Then I will introduce the model I am using, which is the MMG model. I will introduce the equations of motion, how forces and moments are calculated for use, the hull derivatives and hull forces, the proportional forces, the rudder forces, and finally how the equations of motions are rewritten so that they can be solved in the body fixed frame. Finally, I will present the result of the solved model for the turning circle maneuver. So, system identification, the goal is to predict the hydrodynamic derivatives of the MMG maneuvering model from data that is derived from turning circle tests and zigzag maneuvers. So, this data is fit into the MMG model using a regression model called support vector regression.
Ashwin, like what is
Yes.
MMG?
Yeah, I'll come to MMG. MMG model is a ship maneuvering model proposed by maneuvering model groups, which is a group in Japan.
Okay.
So it's a ship maneuvering model like Apkovitz model, Nomoto model.
Okay.
But it's like more complicated and it mimics the motions of the ship much better than the lower level models. Okay. So the data is fit into the MMG model using support vector regression, and by using support vector regression, we can use something called kernels, and which essentially project the data. The data consists of the velocities and rates from the zigzag and turning turtle maneuvers. They are projected into a higher plane so that they can be separated more easily, and they can be separated more easily by the support vector regression. So one of the problems with system identification is the problem of parametric drift. Now, parametric drift occurs when linear derivatives cancel out during this when performing the support vector regression, and nonlinear derivatives are multicollinear in nature. That means the nonlinear derivatives would be related to each other, and when doing support vector regression, it actually fails to separate these two. So, to solve this problem of parametric drift, the paper I am currently looking at uses something called batching. In batching, you take multiple circle test data and zigzag maneuvers data, we combine them and actually add them together. What this does is it adds non-linearities into the data, which will help when doing support vector regression. After
Ashwin, I just have a quick question here. Are you going to cover parametric drift again?
No. I am just no.
Then I don't think I have understood what specifically you mean by that. Can you be more explicit in that?
Okay. From what so parametric drift occurs when doing support vector regression, when the linear terms, like if when doing this the linear terms get cancelled out, the derivative terms get cancelled out because of the linearity between them, and they are interrelated to each other. So when using kernels, what happens is they will represent the same type of data in a higher plane. So they can't be separated. So that is the problem.
Here is where you might have had an example would have been better. Because
Okay.
I think it's not quite clear what you mean exactly.
Okay, I am not clear about an example either. So I only have knowledge of what was presented in the paper. I didn't look too much into it.
Okay, all right. But that's kind of what you're trying to say is, suppose I have two derivatives,
Yes.
two hydrodynamic derivatives. One is YR, and let's say the other one is YRV.
Okay.
Okay, so I have these two derivatives which I want to identify. So the idea here is, and I think that's also the other portion of the thing which you kind of want to mention clearly. What is your input to your SVM and what is your output which you're trying to get? The input here is the trajectories of the motion and the rudder angle, how you are varying it. Those are your input to your model here. And out of that data, you're trying to predict out what are the hydrodynamic coefficients. So in essence,
yes. So the input vector consists of the velocities and rates plus the coordinates of the trajectory.
and the rudder has to be there.
Yes,
You
and the
want to
rudder.
predict any of the rudder dynamic coefficients.
Yes, and the rudder.
Correct? So
yes.
The idea is that you have these entire time histories you have. From that, you want to identify the coefficients. Now, one might wonder, see, if you have a maneuvering model which already has the coefficients, why should we try to identify them again?
Yes. So the aim is to actually get higher derivatives rather than the lower derivatives that we already have.
No, that's not the aim. And that's where I think you're missing the point. The MMG model, you are using it as a test case for now. Okay, so you're trying to kind of do a proof of concept here where your MMG model represents the real vessel. But in reality, what you will happen is you will get those trajectories from an actual experimental run.
Yes.
Okay, once you get them from the experimental run, we then want to try to identify the coefficients from the experimental run in order to see whether we are able to identify the hydrodynamic coefficients aptly, such that our modeling with the hydrodynamic coefficients will result in a model which is giving closer approximations to our real data.
Oh, okay. So we are proving that the derivatives are correct that we already
Here
have.
you are simply proving that the derivatives are correct, with which what you are saying is, okay, I'm able to identify these coefficients, but in reality, you will be performing this on an experimental data in order to identify coefficients which you probably cannot get any other way.
Okay, so if we have something like a new ship, we can use this method to identify the coefficients.
Correct, exactly. Now you're on track. So we are kind of saying that if I have a ship about which I don't know anything, or say, for example, the KCS ship, I may know the modeling, but my modeling may not match my experiments. Okay?
Oh, okay.
In which case, I might want to identify the coefficients to improve my modeling so that it matches well with the experiments.
Okay. So you are not actually able to get new derivatives. You'll only be able to get derivatives as prescribed by the model.
Correct, as prescribed by the model, precisely.
Okay, okay.
Okay, so I think what you should lead with is the idea that my input is the trajectory histories and the input rudder angle time histories. From that, I'm trying to predict the hydrodynamic coefficients without having to do the regular approaches. See, the regular approach to get these coefficients would be to run an inclined, what you call circular motion test or a planar motion mechanism test. We are not going to do that, but rather have a free running model. Can we identify these coefficients from a free run? That's the problem.
From a free running model?
Yes, from a free running model, which means it's a fully outfitted KCS hull with a propeller and a rudder, and you're trying to run different trajectories. From that, can I get these coefficients?
Okay, okay, yes.
Okay. Otherwise, what's the point? If I were simply trying to predict the hydrodynamic coefficients when I already knew the model, it
Yeah, yeah.
wouldn't help me much. Only if it helps me improve the model.
Yeah,
Is
yeah,
there
okay.
a point of doing this study?
Like, what do you mean by improving the model?
So for example, let us say I am using certain values of YR and YRV, let's say, for
Okay.
example's sake. Okay.
Yes.
Now, I may be able to get a trajectory out when I do a turning circle maneuver. And let's say my trajectory comes out to be some, let's say the steady turning diameter comes out to be some value.
Okay.
But when I do the experiment, it may so happen my turning circle diameter comes out to be a different value.
Oh, okay. So to match your mathematical model, you
Correct.
can
So you want an
derive
accurate
a new
mathematical model for the same ship. You want to achieve that by identifying from the data from the experiments.
Okay.
And a clear example of this would be what Rohit and Sanjeev were looking at. For example, in their ship, which they chose, or Rohit presented last time, the turning circle is what he was using as a basis to figure out what his N delta will be. Because he did not know the value of N delta, he wanted to
Okay.
fix the derivative in such a manner that it will match with the experimental value of the steady turning radius.
Okay.
So here what we are doing is kind of inverse of that. We know the experimental data. Here we have an experiment of our own. And from that we want to make our mathematical model more robust so that it represents the actual experiment in a better way.
Okay. Okay.
All right.
Okay. So I use the MMG mathematical model, and I have the derivatives already. Then I do the turning circle test and the zigzag maneuver test, generate the data to derive the derivatives. So I will explain how the MMG mathematical model is formatted next. So the MMG model is proposed by a research group called Maneuvering Model Group in the Japanese Towing Tank Conference, JTTC. And the model is used because it provides a comprehensive representation of the vessel maneuverability. And in this model, the non-dimensionalization is called a prime 2 non-dimensionalization. That means the forces are non-dimensionalized by half rho L T U square, where L is the length perpendicular LPB, T is the draft, U is the net velocity of the ship. That means both the it's a combination of the longitudinal and sideways velocity. You take this vector sum of the velocities, and the moments are non-dimensionalized by half rho L square T U square. The lengths are non-dimensionalized by L and the angular rates by U by L. Now, the frames of reference, I will briefly explain the frames of reference, which are also different from usual models. So X is pointing up and the space fixed frame O0 has X naught pointing up, Y naught like so. And the body fixed frame for my model is fixed at centerline midship. So it is not at the center of gravity, but at centerline midship. And phi is the angle defined between x naught of the global space fixed frame and the x of the body frame, and it is measured as so. So phi of 0 means it will be going along the x-axis. And now next, an important parameter, drift angle, is also defined. Drift angle is tan inverse of Vm by u. Minus of here it's minus of Vm by u. And Vm is the velocity in the y direction, this V at midship and not at CG. And then we can calculate the V at CG by using this formula Vm plus Xg into R. So in the original, there are multiple papers with different models proposed, and I'll be just following one model, which is the original Yaskawa model. And in that model, the equations of motion, as you can see, are expressed with respect to G, the center of gravity.
Ashwin, can you pause and go back to the previous slide?
Yes.
Here, how is the coordinate frame different than the ones which we have explored in our classes? Is it different?
Like x z is pointing down. What is different is this phi.
It's only a question of representation, right?
Yeah,
It is also
it's just
pointing down here.
yes, but this phi is different.
No, I think the psi is also the same. Psi is always the angle of the longitudinal direction of the ship with respect to the x-axis.
Okay, it's just they flip the representation here. I think that's what
Correct. That's all.
yeah. But here they mark delta like this, but delta to starboard is positive. I
Correct.
mean,
So
port is
here,
positive.
that is the only difference, that the rudder angle is considered positive in that starboard
But
direction.
yeah, yes. But in my when I try to code it up, like port is positive. It follows a proper Z form. So downward Z, yeah. So to port is actually positive.
Okay, when we come to the hydrodynamic derivatives, I think that will be a little more clear.
Yes.
Especially what the value of n delta, what the sign of n delta is, will determine that.
Okay. So as you can see, the equations of motions are expressed with respect to the center of gravity, which I will have to rewrite, and I have rewritten them in the end. The added mass and added inertia are represented by mx, my, and jzz here, and the velocities and rates about the center of gravity ug, vg, and rg. Now x, y, and n are the net forces and moments, and they are about the midship. The Adam's terms are derived using a frequency domain program at the nominal speed of 24 knots.
What is Nm?
About Nm is the moment about midship.
That's
It will
the
be the same as Ng.
Okay.
So the
Maybe now is a good time to quickly go through the audience. Any questions so far? Yes, no.
is there any doubts on this? About x, y?
Ashwin, is that n from on the left side, the equation is that from the midship or the center of gravity?
Yeah, they are actually the same because it's n.
Yeah, right.
Anything else? Okay, so let's move on to the forces and moments. So in the MMG model, the forces and moments are divided into the hull forces and moments, the rudder forces and moments, and the propeller forces and moments. And I will explain how each of them are derived. So going on to the forces and moments acting on the hull. So you can see that the hydrodynamic derivatives expressed as x naught, x beta beta, y beta 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 are all defined with respect to beta, the drift angle, and the non-dimensional turn rate r dash. It's not unlike other models, which is v and r. Here it's defined with respect to beta. And you can see here this rho by 2 term with the non-dimensionalization parameters, and the xh is actually xh plus something is actually given us this whole term, which constitute the hull force and moments acting on the force and moments that are acting on the hull. Now let's move on to the propeller induced force and moments. So the propeller only gives a force along the x-axis defined as thrust. The thrust is rho kt dp power 4 and n square, where kt is the propeller thrust coefficient, which is a function of the propeller advance coefficient jp. And jp, for calculating jp, you need the wake at the propeller, the velocity, the rps of the propeller, and the propeller diameter. Now, a thrust reduction factor of 1 by t is also included to calculate the net propulsive thrust along the x direction. The moments and the y force are 0 for the propeller due to the propeller. Now, let's look at the propeller wake fraction here, this WP. This WP, the wake fraction, actually changes with maneuvering motions because the inflow angle into the propeller changes. So because of the drift, the propeller wake fraction at the propeller actually changes. So to get the wake fraction, you have to calculate the inflow angle into the propeller beta p as this. where this xb, which is the drift rate, minus xp into r.
Ashwin, we
Yes.
will take a pause here. Can you go back one slide?
Yes.
Okay, so you mentioned something about thrust deduction factor, isn't it? And
Yes.
also you have talked about a wake fraction. Now, what is
Yes.
the thrust deduction factor?
Thrust detection factor, like because of the the thrust will be reduced because of the wake, right?
No. So why do we need a thrust deduction factor?
Uh, this is the uh, this is the thrust with just the propeller, and the thrust reduction is with the hull.
Correct. So with the hull, why is the thrust deducted?
Because of the skin drag due to the hull. Skin
Yeah.
friction drag due to the hull. Yes.
Due to the skin friction drag due to the hull.
Yes.
No, but that is part of resistance, isn't it? That does get captured in your resistance term in your equations of motion, which will be that x naught. Can you go back one more slide?
Oh, this x naught.
Yes.
Okay, this is due to the hull.
Yes.
Okay, like because of the hull, the inflow into the propeller will be different.
Correct.
Right? So you need a reduction.
No, that's not the reason why the reduction comes. Okay, so primarily what happens, so when the propeller is acting behind the hull, you're accelerating the flow into the propeller, correct? Now, when we typically compute resistance of a ship, what we do is we typically have a bare hull without a propeller that is
Yes.
towed in a towing tank. Okay,
Yes.
and then the dynamometer is attached to the hull, and that measures the resistance of the hull.
Okay.
Whereas here what's happening is because the propeller is behind the hull, it's kind of pulling the flow into the propeller disc. Because of
Yes.
that, at the stern region of the ship, you typically have a faster flow than what you would have in a typical run at the towing tank.
Okay.
Okay, so therefore there is an increase in resistance.
Okay.
Okay, now instead of capturing that as a part of the resistance, they are taking it as a fraction of the thrust in order
Okay.
to compensate for it.
Yeah. So it's because the flow rate into the propeller is different between the free running and this one.
Correct. Now, can you tell me what is the wake fraction and how is it different from this thrust deduction factor?
Okay. Wake fraction is behind the propeller. So the wake behind the propeller will have a different velocity than the surrounding fluid,
Okay.
which is captured in the wake fraction, I guess.
Why would it be less?
So why would what be this?
Why would the velocity right behind the hull be less?
Velocity behind the hull is not less, right?
Then why do we need a thrust wake fraction? Does anybody else want to help him out here? What is the wake fraction?
Ashwin,
Yes.
I tell about something related to the wake fraction. So I am studying from that wake fraction means the speed of the propeller when related to the water is lower as considered to the absorbed speed of the propeller.
Oh, okay.
So the ship speed and the speed at which the water is coming into the propeller, or if the propeller were not there, the flow velocities at the propeller disk would be lower. But the question is, why would it be lower?
Sorry, can you repeat that? What will be lower?
But if you had the hull, and if I were towing it down there, towing back, okay?
Okay.
And the ship was moving at, say, 10 knots.
Okay.
The velocity at the propeller disk, when the propeller is not there,
yes,
it will be lower than 10 knots.
Why would it be lower than 10 knots?
Precisely the question. You have now asked a good question. Why would it be less than 10 knots? Anyone of our group members want to have a try at it? No? Nobody wants to give it a try? It's because the flow is separated. The flow separates from the boundary layer of the hull. On the separated flow will always have a velocity which is lower. If you assume that the flow was inviscid, which means it didn't have any viscosity, then you would have a flow which is moving at the same rate as the body is moving forward. Okay? And that is what gives rise to what is called as the pressure drag. This lower velocity and lower pressures is what will cause what is known as the pressure drag on the vessel. Okay, but since your propeller will be operating at that region, you kind of need to know what is the velocity at that point, which is why you are using this wake fraction with respect to the ship speed. So see, the ship is moving with a speed of u in the forward direction.
Okay.
And the flow at the back of the propeller, we can consider it to be u times 1 minus Wp. In reality, this flow will vary across the propeller disk completely. It's not going to be one number. It will vary across the complete propeller disk. Depending on if you are at the bottom of the propeller disk, you may not see much difference. But if you're at the top of the propeller disk, you may see a much lower velocities. And there'll be a distribution. But we kind of try to account for all of that in one factor as a bulk. And we are saying as if the average velocity through that wake region where the propeller would have been situated, due to the presence of the hull, the fluid flow is slowing down, and that slowdown factor is Wp. Okay?
Yeah, okay.
Right. Okay, is what I'm talking about clear for everybody else too?
Yes, sir.
Do I have only one audience?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, please continue, Aswin.
Ashwin, I have also one doubt.
Yes.
Please go back to the backside. Thrust reduction factor is the 1 minus T or only the TP?
It's 1 minus T. T is whole number between 1, 0 to 1, I think.
No, what he's asking is, when you define thrust reduction factor, is it T which is called thrust reduction factor or 1 minus T which is called thrust reduction?
Oh, I think T is the thrust reduction.
Correct.
And 1 minus T will be the net. You have to multiply with U. I mean, multiply with this. Okay. Anything else? Okay, I will continue with the propeller wake fraction. So, because the propeller wake changes with the inflow angle, I have to calculate the this 1 minus Wp with respect to the Wp at 0 wake. I mean 0 angle.
So what is the WP0?
Rudder 0.
No, it's not rudder 0.
Wait.
Like a straight line motion. Sir.
Like, in straight line motion, it would go straight, so that the beta will be 0.
Correct. So there is
That
no
is the
vehicle.
Yeah, so you need, for different betas, I need to know what the wake fraction is at the propeller. So if you plot it, you will see that it's different for different positive and the negative beta p. So that means in this approximation of the wake fraction that is described in the paper, the values of C1 and C2 are different for positive and negative beta p, which in turn affects the net XP. So which means depending upon the rudder, if it's like the delta is positive or negative, the net thrust is different once
So
it's attains steady
should it
state.
not be symmetric? Why should it not be symmetric?
Yeah, it is not symmetric here because of the propeller interaction with the rudder.
Correct. Because the propeller is rotating one way, it will
Yes.
not be symmetric.
Yeah, and this is messing with my turning radius thing.
Yes.
So that is why it was actually not being symmetric. Okay, I'll get to that later. So next is the rudder-induced forces and moments. So to calculate this, we need the normal force on the rudder Fn, and the normal force on the rudder we need it and we need to calculate the normal force for a given rudder angle delta. And in this formulation, the tangential forces are neglected here, but are compensated in these coefficients, which I will explain here. So in this, Fn is the rudder normal force and Fn cos delta is the y component. So yr will be minus Fn cos delta. And there is an added term AH here. AH is the rudder force increase factor, and there is an NR. The NR is the turning moment, which is Fn cos delta times this length. This length is captured by XR, the longitudinal coordinate of the rudder. These should also be non-dimensionalized, so I'm dividing by L. That's why there's an X dash here. And XH is the steering force center of the hull. So because of the rudder interaction, there will be this Fn cos delta, and an additional Y force will also be produced due to the interaction between the rudder and the hull, which will be in the opposite direction. And this also has to be subtracted from the moment, and this is what this XH does with the this reduction factor. So the net moment will be this one minus this one, which is captured in this equation. And the XR will be 1 minus TR, which is the steering reduction. Fn sine delta will be in the opposite direction, and this is the reduction due to that. And the reduction term is also added to capture the XR.
So the steering resistance deduction factor, that is coming primarily because of which phenomenon? The TR.
This TR.
Yes.
So that, it is due to the rudder, and I think it's due to the flow velocity changing.
No, is it because of the tangential force on the rudder which you are not considering? Is that a factor to account for that? Or is it a factor which is something else?
I'm not sure about
Okay,
that.
I want to check up on that.
Okay.
All right, and similarly AH,
but I think it's mostly due to this tangential forces being taught, and they're compensating it here. That is what is said in the paper. Yes.
Just be sure that that is the case, okay?
Okay, yeah.
Yeah, I think so too, but I'm not remembering it quite well right now.
Yeah, they are doing a lot of like these factors there are a lot of factors that is accounting for this, because they are neglecting these tangential forces.
Yes, so you want to be, that's why you have to kind of understand what is the physics behind them. That will tell you what these signs should be.
Yeah, the problem is this reduction. Yeah, in the original paper it's given as 1 plus AH, right? But AH is in the opposite direction, so it should actually be 1 minus AH.
No,
should also
but
be 1
the
minus
force
AH
is
here.
negative delta Y because it is in the opposite direction. You have to look at the conventions. You have to kind of make sure that in a conventional sense, it should add to the minus y.
See, Fn cos delta is this, and AH Fn cos delta is this.
Correct. It kind of makes sense, right?
It should be in the opposite direction then, right? So it should be 1 minus AH.
So AH is positive or negative?
AH is positive, and 1 plus AH is 1.36, is AH is 0.36. Is what is given in the paper. 1 plus AH is greater than 1.
Okay, which means that the rudder force, so the net force is coming out to be greater than Fn cos delta.
Yes. But in this, here it's given minus y. I'm not sure which one to follow to.
Yeah,
using
the paper again. I don't remember off the top of my head.
Yeah. So in one paper it's given minus AH, in one other paper it's given 1 plus AH. But in the tables that are given, they have given 1 plus AH. They have not given AH separately. 1 plus AH, they have given it as 1.36.
Okay. Oh.
Yeah, so this XR and XH does the same thing. XR is the length till here, XH is the length till here, and multiplying by the force, you'll get the net moment due to the rudder. Now, calculating the normal force on the rudder, F.
Aswin?
Yes.
Why we are considering the parameters? Is this the non-dimensional force and moment, or only the force and moment?
This is Fn is non-dimensional. To make it dimensional, I multiplied by this according to the primitive non-dimensionalization. Now, Fn, it can be calculated as dimensional or non-dimensional. In the paper I'm following, they calculated it in a non-dimensional manner, and they are making it dimensional here by multiplying by these factors.
Okay.
So the non-dimensional force, the normal force on the rudder is given by this formula, which is AR is the profile area of the movable part of the rudder, and they're non-dimensionalizing AR by dividing by L and draft. F alpha is the rudder lift gradient, multiplying by UR. Now UR is the net outflow coming out from the rudder, which consists of this small UR, which is the longitudinal component, and the lateral component VR. The net one is capital UR. So UR square times sine alpha R. Alpha R is defined here as the angle between the rudder and the net component. And alpha R is computed as this delta, which is the rudder angle, minus tan inverse of V by R. So which will get delta is equal to this, and tan inverse of V by R is this. So subtracting, you'll get alpha R. Now this UR and VR are calculated by using these formulas, which are directly given in the paper. So here what is happening, UR is basically derived by taking into account the diameter of the propeller and the total area of the rudder, the flow outside the actuator disc and flow inside the actuator disc, and finally you can derive this formula, which I'm not going to go into. And VR is also an approximation using a flow straightening coefficient gamma R, and which is a function of the drift angle as well as the non-dimensional R and LR. Here LR is the effective longitudinal position of the rudder. That means from midship, LR is the distance between the midship and the rudder position, which is again non-dimensionalized by the total length of the midship, which is L. Now, yes?
Is that, are you sure it is the longitudinal coordinate of the rudder position? I think it might be different because that is XR. LR might be slightly different.
Yeah. This said effective longitudinal coordinate.
Correct.
It is slightly greater than 0.5. LR is 0.755.
Yeah, effective of what? That's something which you have to look at. Okay.
Okay.
We have to get a sense of these things. I'm asking you to kind of understand each of the coefficients, why they are coming, because then we'll be able to better appreciate whether these value signs are correct or wrong. Otherwise, it will be a hit and trial, and I don't want to do that. I want to have a physics-based approach rather than a
like it's not being explained very well in just one paper. It's like
correct.
strewn about in multiple papers. So I
No,
looked up some.
one second. I think if you look at that 2015 MNG model paper, I think there the definitions are at least clear to my knowledge.
Yeah, I took the definitions from there, and these are what were given. I read that paper. It says effective longitudinal coordinate LR. They're not going too much into it.
Of what
So
LR?
if I had more information, I would have written stuff down here. But
okay, all right. 1 minus W, is the W the same as W which we...
This is WP. So what is happening is they want 1 minus WR, and they define this epsilon E as a constant. And they multiply by 1 minus WP to get 1 minus WR. To multiply to get this coefficient.
What you see there is 1 minus WP in that expression?
Yes, this is P.
Okay.
And this epsilon they are saying is a constant.
They're assuming that that doesn't change too much as you change.
Yes.
Okay.
And they're also using the ratio of the diameter to the span to get this.
Yes, that kind of explains the fact that this factor which we have seen in class only corresponds to inside the actuator disk, and outside it, it is free stream velocity.
Yes. They're also using this 1K constant, which captures how much higher the velocity outside the slipstream is with respect to inside the slipstream, which is also, they got this from a captive test.
I think that factor even we had in our class notes, but we kind of took an empirical approach to it. That's kind of trying to understand as I move further away from the propeller disk, how much is the increase or decrease in velocity. It should be an increase in velocity because the slipstream actually contracts.
So in this paper, they are assuming it's linear, and K is defined as Kx by epsilon. Kx is that linear factor by how much it increases. Okay, and now moving on. These are the final equations of motion that I have rewritten into the body coordinate frame from the previous center of gravity frame, and these are what I will be solving using a fourth-order Runge-Kutta method, and I have performed a turning test circle simulation. So these are the results I got for the turning circle maneuver. As you can see, for a plus 35 delta, the rudder angle, you have a much bigger critical diameter than the minus one. You can also see the variation in the surge speeds, these two lines. Surge is going, the speed is going from 1, this is non-dimensional, or everything is non-dimensional here. This is also non-dimensionalized, y0 by L and x0 by L.
How much is the difference in the steady turning diameter or radius?
This is approximately something like 1.5, and this is more than 1.5. This is about 2, and this is 1.5. So about 0.5 L. I think this is just too much.
Yeah, I think that's quite a large variation.
Yeah, I also think it's quite a large variation.
Okay, I mean, it should be different, but not this different, I would believe.
Yes. I think most of the parameters I'm using, I'm just not sure of if they're right or not.
Okay, you and I will need to compare our models, because I'm getting one as 3.38 as the diameter, and the other one is 3.68.
Okay, I think that is better actually. In the actual one, in the actual one, it's supposed to be somewhere around 3, the tactical diameters. So I'm not sure where I'm going wrong.
Okay, so maybe you and I can compare models later.
Yeah, okay. Okay, that's it. I've been stuck at this stage trying to get this thing to work for some time now.
Okay, so what I'll do is maybe you can create a GitHub repository.
Yeah.
And upload your code to it, and I'll create a separate branch on it and put mine there.
Okay.
You can try to compare the two and see where the difference is coming and whether which one of the two is the best and whether can we mix and match and get any better results.
Okay. Yeah. One more thing. When I tried to change the radar midway through a run, the model just doesn't respond. It just keeps going with the initial radar.
Yes. So
It's
you're
like the model is
no. That does that mean you're unable to do the zigzag maneuver?
Yeah, that means I'm unable to do the zigzag maneuver.
Okay, then that also is something you have to look because I'm able to do the zigzag.
Okay.
So
Okay.
hopefully that will give you a sense of what's going on.
Yeah.
Okay, so that is fine. The other thing which we want to do here, I think it's a good time to talk about, is we want to kind of also look at comparison with experimental data.
Yeah, experimental data, I'm keeping on comparing with all the experimental data, and in experimental data, the tanning radius is coming out to, tanning diameter is coming about to 3.
To
About
3.
3, yeah, 3 something. About a little bit about 3.
Where are you getting the source? What is the source of the data?
You had sent me a paper.
That paper, the Yasugawa paper.
Yeah, the most recent one you have sent me.
Okay, yes, but that one, the most recent one that I have sent you, it only has a simulated result.
Yeah, not the actual results. It's a simulated.
Yes, but the second paper which you are following from Yasugawa for the case, I think that has experimental values reported in it for the turning circle. So you might want to also compare, kind of put it on the plot as well, and just to see whether does it.
Okay. Yeah, I'll do it.
Okay, and there is a good program called Web Plot Digitizer. If you're looking for one to digitize plots, that's a good one.
Okay, they have a free running data.
Yes, they have a free running data. Correct.
Yes, they have the free running data. Yes, and it's about 3.5. 3.5 minus about 0.5. Yeah, 3.
Yeah.
About 3. It's coming about 3 years.
Yeah. So maybe you can digitize that, and then we can kind of compare.
Yeah, we can compare.
Okay. Can you go back to your presentation?
Yeah.
All right. Up till here is good, but can you kind of tell your friends what is the next plan of action which you're planning to do?
Yeah. So the next step of action would be to get the data, verify the data using verify it using the other papers and experimental data presented in the other papers. Then I would take the data from these maneuvers and try to get back the derivatives. The derivatives, these derivatives, I'll try to get them back and compare with what I have input and what I have output. Calculate the error and see how best to fit the model.
We can also try something else as well in addition to that.
See, one more thing. This is just like non-dimensionalized with respect to beta, right? So what Yatsugawa and those people have done is, because most of the experiments use XBB, XUR, they have actually made another model with those coefficients. So I think it would be better to use those.
Which paper is this? The same one which I have sent you at the end?
No, the latest Yatsugawa paper. This one.
This is the MMG 2015 paper.
This is 2014 paper, and in this paper they have used VR.
Yes, but I don't think we have these.
I don't think we have XBB and.
No, I don't think you have these coefficients for the KCS for which you want to do.
Yes. So I don't have these for the KCS, but there I found one other thesis which did it for the KVCL, the other ship.
KVLCC.
Yes, that's it.
Okay. Yes, but we are primarily interested in the KCS because we want to kind of be able to do the experiment on our cases that we are building. So in that sense, we want to kind of focus more on the KCS. So what I'm thinking is twofold. So one is you can identify the coefficients with respect to whatever you have used in your MMG model. Or a second approach might be that, say I construct a Apkowitz model for the KCS shape.
Okay.
You use the data which you are simulating from here, but can you identify the Apkowitz coefficients which will give the best fit to that model? Then you are resulting with a Apkowitz coefficients for the same hull.
Oh, okay. So,
Because
but that is
at the end of the day.
okay.
Got my point?
Yeah, but will Apkowitz model be able to give coefficients that can match this MMG model?
I'm curious to find out.
Okay.
Okay, so one is definitely you can try to repredict what MMG model is using. The other might be to try to figure out. You see, then what can happen if you're, say, able to figure out the Apkowitz model for this ship, then Sanjeev and Rohit can actually dump all the coefficients that they are currently using, and they can go with yours.
Okay.
If we are able to get yours based on experimental data.
Okay.
So we conduct some experiments, get that data. So if we are able to, and the proof of concept will be that you simulate the maneuvers using the Apkowitz model with coefficients which you have identified. Do the trajectories match with the MMG model which you gave as input?
Okay. Yeah.
Right. If they match, then we know that the Apkowitz model performs as well as the MMG model. And that's a simplified model to deal with in respect of parameters.
Yeah.
Okay, so and that can be used by others who are working in the similar lines for a different sort of an approach.
Okay.
So for example, right now Sanjeev and Rohit are tuning it for the radius. They can dump all those coefficients and they can take the coefficients from our data which you have identified for them.
Okay.
That's a nice collaboration which I can see happening between the two different problem statements.
Yes, I also had one more doubt on the non-dimensionalization.
Yes.
What is this U? Is it the full ship speed or the?
It's the full ship speed.
Okay, I have not been using the full ship speed. I have been recalculating the net U at each time.
No, that will be the design speed. You won't change this U because a non-dimensionalization cannot suddenly change halfway through a simulation. It always has to be a fixed number. And the constant number there would be the design speed of the vessel, which will be the...
Okay, I have tried both U and the design speed. I didn't see much change though. And it says that the U shouldn't actually change that much. It should actually like remain somewhere at 1 even while doing the maneuvers.
Yes, because when you take
happening.
square root of small u square plus small v square with the sway and the surge combined, the velocity should be the same as what it was originally. But
yes,
in a linear model, in a nonlinear model, it will not exactly be the same. And in fact, when you look at my code once we upload it and you look at the zigzag maneuver, you will find that there is a slight decrease. And it will not exactly be 1 all the time.
Okay.
Okay, but it will be close to 1. It will not be too far away.
Okay.
Okay, Sanjeev, thoughts on being able to collaborate with Aswin on this?
Yes, sir, I think it would be good. I was also trying to develop the MMG model a while ago, and then we put it on hold. So.
Okay, so I think that would be, so what we can have is both of you can kind of take a look at it together. Okay, so then once you create the repository, Aswin, I'll add you, Sanjeev also to that repository.
Yeah. Should I make the repository or will you be making the repository?
Okay, I'll make the repository to keep things straightforward. I'll make the repository and then I'll share it.
Okay.
Okay, all right, sounds good. Any other questions, doubts?
This is the other paper that I found.
Okay, whose thesis is this? And where is it from? TU Delft.
Yes.
Who was his advisor?
And he actually did the model comparing maneuvers with MMG data. He has already done everything for that other ship.
This is for which ship? KBLCC.
Yeah, he has the UVR, YVR, and
Okay.
he also has the
Zigzag maneuvers.
zigzag maneuvers. He did it for different aspect ratios.
Okay. All right, sounds good. I think that's a good piece of information to have in order to check up on. Okay, but we are more interested in the KCS dynamics.
Okay, yeah.
Okay. Yes, any other questions, comments from the other members? I have not seen a lot of activity from you guys today. Can I have everybody's videos on, please? So, no questions? No questions? Come on, he either has to be a terrific presenter or one of the worst presenters, or none of you to have any questions. Okay, all right. What I'm going to do is I'm going to stop recording now.